ahead and get started. I want to thank everyone for taking the time to participate in today's Snack and Learn webinar. My name is Mark Longtine, and I'm very excited to have the opportunity to talk today on the 51st anniversary of Earth Day. I'll be presenting aspects of the risk assessment addressing mining-related impacts on the Kuskokwim River associated with the Red Devil mine in Alaska. A couple of housekeeping items. There will be a Q&A session at the end of the presentation. If you do have questions, kindly write your questions in the questions box of the control panel. Also, a copy of my presentation slides will be available for download in the handouts box in the control box. So with that, let's go ahead and get started. So I'm a professional geologist. I'm based out of WSP's office in Seattle, Washington, in the United States. Prior to becoming a member of WSP USA, I was with Ecology and Environment Incorporated, which was acquired by WSP last year. Since starting working for Ecology and Environment in 1994, I've worked on a wide variety of projects, including assessment and remediation of abandoned mineland sites across the western United States. For the Red Devil mine site, I served as technical lead and/or project manager for various stages of the site characterization and remediation studies. And as part of that work, I worked closely with human health and ecological risk assessors. The risk assessors that led the effort at Red Devil Mine are not currently employed by WSP, so in their stead, I'll do my best to convey the key aspects of their contributions to the project. Not being a risk assessor, I won't discuss risk assessment in detail. However, I will be talking about key aspects of the site characterization and other lines of evidence that were used to inform the assessment of the site. A few words first about WSP's global risk assessment practice. Of course, risk assessment is an interdisciplinary enterprise, and WSP's global risk assessment practice encompasses expertise in toxicology and all the other various disciplines and skills listed in this slide. The risk assessment effort at Red Devil Mine is no exception. I'm happy to note that with the very recent onboarding of EarthCon and Golder, WSP's global toxicology and risk assessment practice now includes more than 70 staff. Our risk assessment practice endeavors to meet WSP's goals of promoting future-ready core values, including for this project, well-being and diversity. A quick overview of what I'll be covering today. I'll start with an overview of the Red Devil mine and the Kuskokwim River, and I'll talk about key aspects of the site characterization and risk assessment. I'll talk about challenges and innovations that we brought to bear to meet those challenges. And I'll close with outcome and takeaways and a Q&A session. Where is the Red Devil mine? Red Devil mine shown here in the red star is an abandoned Mercury mine at a remote location in the Kuskokwim Mountains of southwest Alaska in the United States. It sits on the bank of the Kuskokwim River in a generally sparsely populated part of Alaska. However, the mine site is located just about 2 kilometers upriver of the village of Red Devil. The mine sits on land managed by the United States Bureau of Land Management. The Kuskokwim River is quite a large river. It's the second largest river in Alaska. You can see here the river and its many tributaries. This inset map shows the location of the Kuskokwim River drainage basin. Key aspects of the Kuskokwim River are listed here. Important to this talk is that fish caught from the river represent an important source of subsistence food for local residents. The Red Devil mine, during its period of operation between 1933 and 1971, was the largest mercury mine in Alaska. It's one of a number of mercury mines in what's referred to as the Mercury Belt in the Kuskokwim Mountains. At the Red Devil mine, they did surface and underground mining, and they performed on-site milling and thermal processing of the mercury ore. The resulting waste rock and tailings were disposed of throughout the valley of Red Devil Creek, which is, the creek is out of view in this slide, but it flows right through the main processing area here and empties out into the Kuskokwim River, which you can see in the background here. The mining and ore processing resulted in metals and petroleum contamination. The primary metals of interest, the contaminants of concern, are arsenic, mercury, and antimony. And those contaminants affected tailings and waste rock, soil and groundwater, surface water and sediment in Red Devil Creek, which you see coursing through the main processing area, and again discharging into Kuskokwim River here. And Kuskokwim River sediment also are impacted. This contamination was the subject of studies beginning in 1971 by the BLM and others, and limited cleanup activities by the Bureau of Land Management, or BLM, which included demolition of buildings and tailings management. In 2010, the BLM contracted with WSP, then Ecology and Environment, to perform a CERCLA, that's a Comprehensive Environmental Response and Compensation Liability Act, a remedial investigation and feasibility study, or RIFS, and associated with that, human health and ecological risk assessments. We'll be focusing today on contamination in the Kuskokwim River from the mine. The tailings and waste rock are eroded and transported by the creek, shown here and here, discharging into the Kuskokwim River, forming a delta in the river, and migration of contaminated materials from there impacts some downriver areas that I'll talk more about in future slides. So we performed the initial remedial investigation, and as part of that, the baseline risk assessment. That risk assessment was performed following standard guidance from the U.S. Environmental Protection Agency and the State of Alaska Department of Environmental Conservation, and generally used as standard and default assumptions. We evaluated for human health, which I'll be focusing on in this presentation. For human health, we evaluated potential future residents, recreational and subsistence users, and potential future mine workers. We looked at on-site subsistence activities and direct contact with the various media and consumption of wild foods, including fish, and drinking of groundwater and the inhalation pathway addressing volatiles and particulates. In short, the initial baseline risk assessment found unacceptable cancer risk and or toxic hazard in all of these media. The remedial investigation identified data gaps associated with Kuskokwim River sediments, and there were associated uncertainties in the risk assessment. So that led to a performing of a remedial investigation supplement. Key data gaps were the extent of mining-related contamination of sediment in the Kuskokwim River, and bioavailability and methylation potential and bioaccumulation of mercury in that sediment, sediment toxicity, and subsistence consumption of fish caught from the Kuskokwim River. So on those first data gaps, we did quite a bit of additional sediment sampling in downriver locations and additional sampling where we had done some of our earlier sampling during the original RI, or remedial investigation. Bottom line result is that we found that concentrations decrease from the location of Red Devil Creek Delta down to background levels within about a kilometer of the Red Devil Creek Delta. These samples here represent background, and we see increases in concentrations associated with other mineral occurrences at these downriver locations. These bar graphs are showing total metals concentrations for antimony, arsenic, and mercury. We tackled mercury methylation using several different lines of evidence. We sampled directly for methylmercury in sediment. We found that between the original RI samples and the supplemental samples, that fewer than half the samples had methylmercury concentrations greater than the background value. And for perspective, we compared those concentrations to a US river average value. And the concentrations in the Kuskokwim River are generally low relative to that national average. We used several different lines of evidence, including selective sequential extraction procedure laboratory results to evaluate mercury solubility behavior. And we found there that most of the mercury in sediment is sparingly soluble and therefore not readily bioavailable. We note, however, that the soluble fraction is nonetheless elevated. However, it doesn't appear to be methylating to a very high degree, and we attribute that to conditions in the river near the mine site, which are not conducive to methylation. Typically, mercury methylation occurs in reducing environments associated with wetlands. It occurs in other environments as well, but we see a lack of wetlands, and we see instead coarse substrate and very well oxygenated conditions. The final line of evidence has to do with periphyte and tissue sampling performed by BLM. The bottom line is related to mercury methylation, is that methylmercury was not detected in those periphyte samples at the base of the food web. Real quickly, we looked at sediment toxicity. We used 28-day growth and survival tests using Hyalella azteca. We found low to moderate effects on survival and growth and/or biomass in 3 of the 10 site samples. We found no relationship between those effects and sediment concentrations of the contaminants of concern or other site-related metals. It appears that the effects were instead due to sediment texture and/or total organic carbon levels. Concurrent with our work, the BLM, in cooperation with the U.S. Fish and Wildlife Service and the State of Alaska Department of Fish and Game, performed some regional river investigations. The primary goal, or the general goal of the studies, was to relate mercury and other metals found in subsistence fish species to the locations and movements of those fish within the Kuskokwim River system and its tributaries. Specific elements of the studies involve fish tissue sampling. Adult northern pike and burbot and Arctic grayling and sheafish were all sampled. Northern pike and burbot were captured and tagged with radio transmitters. Non-lethal biopsies were taken and analyzed for metals. And after release, the fish were tracked using ground and aerial surveys. Forage fish and benthic macroinvertebrates, as well as surface water and sediment, were sampled for metals from tributary streams. Community health assessments for benthic macroinvertebrates were performed in tributary streams, And finally, as I mentioned in a previous slide, periphyton tissue was sampled and analyzed for total metals, as well as inorganic arsenic and methylmercury. Findings from those studies that are applicable to Red Devil Mine are listed here. They found that mercury levels in pike and burbot from the reach of the river that includes Red Devil Mine are low compared to other reaches and other tributaries. Only about 10% of the burbot and 40% of the pike captured in that reach remain in that reach. The low fidelity of these species reduces their exposure to mercury and other contaminants from Red Devil Mine. That low fidelity is likely due to habitat characteristics near the mine, which include strong current, high turbidity, linear shorelines, and low density of shoreline wetlands. So we gathered up these multiple lines of evidence and concluded that collectively the site characterization and the regional Kuskokwim River investigations indicate that Red Devil Mine metals impacts on river sediment extend a limited distance, about 1 kilometer downriver from the site. Within that reach, the river is not attractive habitat for subsistence fish species, and therefore Red Devil Mine is currently not a significant source of mercury or other heavy metals in subsistence fish in the middle Kuskokwim River. So concurrent with, or I guess following up on the RI supplement, we performed a risk assessment supplement for both human health and ecological risk. I'll focus my talk here on the human health assessment. The methods used were consistent with the original baseline risk assessment. A couple key differences were that regional fish tissue data as part of the regional studies were used to assess risk from fish consumption. We assumed that metals in subsistence fish get their body burden from the Kuskokwim River as a whole, not just from near the site. We calculated exposure point concentrations based on those regional data for northern pike, burbot, Arctic grayling, and sheefish. And consumption rates for residents in the Red Devil Village were based on harvest rates published by the Alaska Department of Fish and Game. To address sediment exposure, we addressed that river reach in which the elevated metals concentrations are likely attributable to Red Devil Mine and not to other mineral occurrences. That approach accounts for, we accounted for important subsistence user practices, which includes, importantly, seasonal shoreline-based gill netting for salmon. And the exposure point concentrations were calculated using a weighted approach that accounts for the wide range in sample density and concentrations. We focused most of our sampling near the mine site, and we have fewer samples in downriver locations, and so we accounted for that with that approach. Key findings regarding risk of fish consumption. We found that the potential exposure to methylmercury and arsenic from fish consumption results in cancer risk that's above both Alaska Department of Environmental Conservation and US EPA cancer risk levels, and that's primarily a function of arsenic in northern pike and whitefish. Non-cancer hazards were above Alaska DEC and EPA standards, and that was driven primarily by methylmercury in northern pike and both arsenic and methylmercury in whitefish. Importantly, the cancer risk and non-cancer hazards from fish consumption are based on regional conditions and are not tied specifically to Red Devil Mine. And this is consistent with a consumption guideline advisory published by the Alaska Department of Health and Social Services in 2016 for northern pike based on their methyl mercury levels. As regards sediment exposure, we did find that exposure to Kuskokwim River sediment near Red Devil Mine results in non-cancer hazards that do not exceed acceptable hazards for based on US EPA and Alaska DEC limits. However, for cancer risk, we did find that for residents and recreational subsistence users, cancer risk is slightly elevated above the Alaska DEC standard of 1 times 10 to the minus fifth excess lifetime cancer risk. Briefly, for ecological receptors, we found only marginal risk to some aquatic dependent wildlife from river sediments near the mine. So this led to our development of our evaluation of a range of remedial alternatives for Kuskokwim River sediments, which were presented in the feasibility study supplement finalized in 2019. Those alternatives were incorporated into site-wide remedial alternatives that are protective and cost-effective, and presented in the proposed plan that was finalized late last year. Key takeaways. For this site, we drew on multiple lines of evidence, advanced risk assessment approaches to develop a refined conceptual site model, led to a better understanding of the influence of regional conditions on mercury and other metals in the environment, including, of course, fish. And that ultimately informed a more targeted risk assessment approach that we use to develop targeted, protective, and cost-effective cleanup approaches. So by taking these extra steps and applying advanced risk assessment methods, we developed a sound and practical cleanup approach that's protective of unique subsistence lifestyles. This is consistent with WSP's future-ready core values of promoting well-being and diversity, as well as the United Nations Sustainable Development Goals, including good health and well-being, clean water, life below water, and life on land. So with that, I want to take just a minute to thank the organizers of this Snack and Learn series, and the many members of the Red Devil team, including WSP and BLM staff. I want to thank the agencies and the many subcontractors. The list of individuals is way too long to list them all, but I do want to give a special acknowledgement to the risk assessors who developed the risk assessment for Red Devil Mine. They include former ED employees Stephanie Buss and Carl Mock, and former BLM risk assessor Doug Cox. So with that, if there are questions, I'll do my very best to answer them. In addition, if there are questions about some of the details covered or not covered, but additional details can be found in all the supporting site documents that are maintained by the Bureau of Land Management and in an administrative record. You can find those documents at this URL here.
Thank you, Mark.
Thank you.
Apologies, sorry. So thank you for your presentation. Just 2 housekeeping items again. You can log your questions in the question box on the GoToWebinar platform, and you can download the PDF version of the presentation from the handout box. We have quite a lot of questions coming in. I will start with the first one. Was surface water assessed?
Yes, we looked quite a bit at surface water quality and discharge rates in Red Devil Creek as part of the remedial investigation and subsequent baseline monitoring. And we also looked indirectly at surface water impacts within the Kuskokwim River. What we found is a water quality within Red Red Devil Creek itself does not exceed the surface water quality criteria, and impacts of discharge of that surface water as well as groundwater into the Kuskokwim River but because of the relative contribution of discharge from surface water and groundwater into the river, the discharge of surface water and groundwater into the river is on the order of 4 or 5 orders of magnitude below the flow rate in the river, and so any possible impacts of surface water or groundwater on the river surface water quality would be indiscernible.
Thank you. There is a question here to clarify mercury methylation. What does it mean?
Thank you. That's a really good question. I should have covered that. So it's important to understand that mercury comes in a lot of different forms in the environment, including the mineral form. And the original form of mercury at Red Devil Mine is predominantly in the form of a sulfide mineral called cinnabar. When that form of mercury and other forms of mercury are oxidized and exposed to just the right conditions, and which often or typically includes assistance from bacteria, that mercury can be combined with methane, and that combined form is called methylmercury, and methylmercury is the most bioavailable and toxic form of mercury in the environment, and hence it's really important to understand what the methylmercury concentrations are and what the processes might be to methylate mercury in the environment.
Thank you. Next question: How did you derive your target cleanup objectives for arsenic and mercury? Did you complete bio accessibility testing, for example, to develop CSM?
I think I know what you're asking there. We did perform some in vitro bioaccessibility testing for arsenic. Now, at the time we did that, which was during the remedial investigation, there was not a standard US EPA methodology for assessing in vitro bioaccessibility. So those results were used just to inform, as part of our uncertainty analysis. What we found is what is common at a lot of mine sites, which is that only a fraction of the total arsenic is bioaccessible. Similarly, we've used selective sequential extraction methodologies to not directly assess bioaccessibility, but to assess solubility behavior, which is directly linked to its bioaccessibility.
Thank you. Next question. Do response action include any sediment remediation, and if so, for which pathways?
Yeah, good question. And maybe what I'll do is go back to a slide that where I can speak to what the preferred alternative is. The preferred alternative will include excavation of all of the tailings and waste rock and contaminated soil within Red Devil Creek Valley. In most locations, that'll mean excavation down to bedrock. Those excavated materials, as well as materials excavated from the Red Devil Creek Delta and at focused locations downriver. All those excavated materials will be consolidated into an on-site repository that'll isolate it from direct contact as well as from possible surface water and groundwater infiltration and erosion. So I think I missed part of that question. I'm going to ask you to repeat that, Sharon.
Sorry, I was on mute. I will move to the next question because we don't have a lot of time. If it's okay, you can follow up directly with this person.
Yes,
We'll go to the last question. Can you briefly speak about the level of support you have from impacted stakeholders in implementing the cleanup action plan?
The BLM, with our support, has been extensively engaged in community interactions. Our company prepared a community involvement plan, and the BLM's interactions with community have included multiple on-site and during COVID virtual community meetings at various points along the process to present updates and also to present the proposed plan, essentially.
Thank you. We have a lot of questions and very nice feedback for a great presentation. Apologies for not getting back to all of you during the live session. Mark will follow up directly with each one of you for your questions. So apologies for this and thank you for logging the question. We are at the end of our webinar session. I would like to thank all the attendees today for joining us. Please feel free to follow up directly with Mark via the contact details that are now showing on the screen. And thank you, Mark, for a very good presentation. It was very interesting to hear, and it was nice working with you. Thank you.
Okay, thank you very much. Thanks, everyone.
Thank you. I will wrap up the webinar now. Thank you.